cell proliferation pathway. And this is a very good place to be able to review some concepts that we went over last week as far as cell signaling. Here in figure 1022 we see, oh look here, we have a tyrosine kinase receptor. So this tyrosine kinase receptor you can review, well, they begin by dimerizing once the ligand is actually bound, and then we have the autophosphorylation process, which then activates a certain activator in the signaling pathway. And so this leads us, this is the cell proliferation signaling pathway, and the activator in this pathway is the RAS protein. Okay? The RAS protein, which is made by the RAS gene. RAS gene is considered an oncogene. So basically what an oncogene is, it is a gene that once the mutation occurs, you have a perpetual activation of this particular protein. Okay? In this case, the active form of RAS is a phosphorylated RAS protein. So if you perpetually have the RAS protein phosphorylated, and this happens because of the mutation that occurs within the oncogene itself, it allows for the signaling pathway to continue on uncontrollably, and that leads us to the formation of a tumor. Okay? So basically when you have, to give you a car analogy, when you have the gas pedal perpetually on go, it's just going to keep going and going and going until basically you have the death of the car, so the crash of the car against God knows what. Here the same basic concept applies as well. You have the RAS protein, which is essentially an oncogene. And so you have the proliferation of these cells using this pathway, and it's done uncontrollably because the activator in the process, the beginning of the process within the cell, actually doesn't allow for the stopping of this process. Okay, because it doesn't actually end up getting deactivated. Okay, so an oncogene is essentially perpetually on, and because of the fact that it's perpetually on, it allows for the tumor formation to occur, for cancer to occur. Now, with tumor suppressor genes, we have tumor suppressor genes such as retinoblastoma gene, and we have the p53 gene. And here we have our p53 protein, which is made out of our p53 gene. So normally p53 functions as a DNA repair enzyme, and it does exactly what the name states. It repairs the DNA strands when there is some type of abnormality that occurs in the process of DNA replication. And so the function of p53 is it triggers enzymes to repair damaged regions, and it can trigger the destruction of damaged cells, okay, if need be. So when we're talking about tumor suppressor genes, they're genes that create proteins that allow for the destruction of cells that could potentially become cancerous. Thus, tumor suppressor genes. Now, when we have the abnormal p53 because of X, Y, Z reason, UV rays, whatever it is, you cause a mutation within the gene which allowed for the p53 protein to essentially lose its proper function. So when you lose the proper function of a tumor suppressor gene, that is when you actually end up getting cancer cells, okay, making the actual tumors, because the abnormality does not allow for the natural function of, in this case, the p53 gene to actually suppress the formation of tumors, okay? And so if you look down here in the last figure of the chapter, you have the key proteins that, went a little bit too far up. So we have key proteins that are associated with these different sets of genes, the proto-oncogenes and the tumor suppressor genes. Okay, and you see this in figure 1024. Okay. Now in the next video, we will be talking about the next chapter in the textbook. That's chapter 11 on meiosis and sexual reproduction.